We open up in this video with an example. We're told here that the final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. So, since there's a claim of the normal distribution, I'm going to sketch the normal distribution and I'm going to locate the mean of 63. And the standard deviation is 5. We are to use this information to find the probability that a randomly selected student scores more than 65 on the exam. So, sketching, I have 63. I'm going to locate the number 65, and I want the probability of more than 65. So, in this case, we want the probability of x more than 65 with the given parameters. So I will go to Start Crunch, key in 63, and so the mean is 63, and the standard deviation is 5 from what we have. So 63 and 5. And based off that, we want standard, and I want greater than or equal to 65. So I'll do that and hit the enter button. This will be 0.3446. So key that in, 0.3446. Then for question B, the probability that a randomly selected student scores less than 85 on the exam. Sure. Draw the normal distribution. You have 63, you have 85, and you want scores less than 85. And let's see, probability of x less than 85 is equal to, going back here, go to 85 and compute. This is approximately 1 or 0 point what? How many nines? So here I have the values here. And for the next part of the question, we have to find the probability that a randomly selected student scores between 67 and 83 on the exam. I'll locate my central value, the mean, locate 67, locate 83, and I'm interested in the region between both. So in this case, I'll go back, choose between. I have the same parameters, but I want to set this to between 67 and 83. So go here, 83, and hit the compute button, 0.2118. So this is the probability between 67 and 83, and that is 0.2118. That is the question in this case, the answer. With that question completed, we now want to go on to finding what we call inverse normal probabilities. Let's give an example. Let's tie it in with something we did earlier. Earlier in this question, we were told to find the probability of x greater than 65. So note something here. This question, I gave you 65. Then you found this answer, 0.3446. That will be the norm. I give that part, you return the probability. Now let's take a reverse, or let's switch the roles. How about I give you the probability and you return the 65? That will be an inverse problem. Let us see what we mean in this case. This said we should find the z-score, which means we are talking about a z random variable, which always has a mean of 0 and a standard deviation of 1. That is the first thing to note, such that the area under the standard normal curve to the right is 0.20. So we want to find a number that we don't know, such that the area to the right would have a probability of 0.20. Should it be on the left or on the right of the mean? That is the first question. Let's reason it out. If I put that number here, you agree with me that the area to the right is bigger than 0.5. Remember, 0.5 starts from here all the way here. Well, the area to the right should not be, because this is 0.20, which is lesser than 0.5. So I know that it's not on this side. So now that I know that it's not on the left, I should know that the missing number is definitely on the right. So I'm going to call that number Z, and I'm going to put a subscript 0.20 there. This is the unknown number. So Z, whose region to the right is 0.20, is what we want to find. How do we find that? Using technology. In order to do that, let's get into StatCrunch. I'm going to call on my calculators, and I want the normal calculator. And in this case, since I'm finding the probability of an area to just the right, so note the area to the right has a size of 0.20, and I want to find that cutoff point here. So I am going to indicate that my mean is 0 and my standard deviation is 1 first. So mean is 0, standard deviation is 1. Then I want an area, in this case, to the right, which is greater than. So I'm going to set that up as greater than. And what is the size of that area to that is greater than? It is 0.20. I will leave this value blank because that's what I want to find. So I'll hit compute and I have 0.8416. So in this case, the number is 0.8416. 0.8416. This is the number such that the probability of Z greater than 0.8416 is equal to 0.20. We can check that, of course, from what we can see here. Probability of X greater than or equal to that number is the shaded area, which is 0.20. With that done, we proceed to the next example. In this example, we have to find the z-scores that separate the middle 83% of the distribution from the area in the tails of the standard normal distribution. Since the standard normal again, I can draw this. I have 0, and I want the middle 83%. So that means I'm going to shade a middle part of the distribution that has a size of 0.83. And I will want to find the z-scores, plural. So it means I want to find this number, and I also want to find this number for the values of z. So let us see what that would be. In order to find the missing numbers, what I need to do is go back into StatCrunch. I'm going to set my mean to 0 and standard deviation to 1. Why is that? That is because I'm dealing with the standard normal distribution. And I would like to set the calculator to a between, because I have the region between, which is 0.83. So I'm going to click on between, and I'm going to do this. I'm going to put 0.83 right here, and I'll hit the compute button. And it will give me those two values, between negative 1.3722 and 1.37, positive 1.3722. So negative 1.3722 and positive 1.3722. This region captures 83% of the distribution. With that said, we proceed to another example. In this example, we are using symbols to find the value of Z alpha when alpha is equal to 0.43. This is going to be very useful for us when we get to inferential statistics. Since it's about the Z distribution, I'll sketch the distribution of the Z distribution with a mean of 0 and a standard deviation of 1. So whenever we see Z of alpha, This might remind you of what we did earlier. Here. So our alpha in this case was 0.20, which means the area to the right, strictly speaking, to the right. So coming back here, we would like to find the area to the right such that it is 0.43. That must be a number somewhere here. So z of alpha is such that the area strictly to the right is of size 0.43. What is that number? That cuts off the upper 43%. That is what we want to find here. So all I need to do is go to Start Crunch, and I'm going to go to my standard case. The mean is 0, the standard deviation is 1, and I want the area to the right to be equal to, I want the area to be right to be equal to 0.43. So I will set that up 0.43 and compute. That number is 0.1764. So you have this is equal to 0.1764. That is the number such that the area to the right is 0.43. Then the next example. Assume that the random variable x is normally distributed with a mean of 45 and a standard deviation of 5. We have to find the 14th percentile. To find the 14th percentile in this case simply means, first of all, we draw the normal distribution. The mean is 45. The standard deviation is 5. We want to find the 14th percentile. The 14th percentile is that number, this number, such that the area below it is 14%. 14% or 0.14. So I'm going to go into Start Crunch. I'm going to set up the right parameters, 45 and 5. So I want standard. So 45 and 5, which corresponds to the parameters given, 5 and 5. And I want less than the area to the left. So area to the left. And I want the size of that area to be 0.14. And I will compute that. That is 39.598. So that is 39.598, approximately 40. So that is that number. So the 14th percentile is equal to 39.598. You may be required to round it off to as many decimal places or even a whole number. So you can adjust accordingly when you're working on a similar problem. Then we proceed to the last example here. This says that the mean incubation time for a type of fertilized egg kept at a certain temperature is 22 days. So the mean is 22. Suppose that the incubation times are approximately normally distributed with a standard deviation of 2. We have to complete parts A through E below. A. Draw a normal model that describes the egg incubation times of these fertilized eggs. This is the normal model with a mean of 22 and a standard deviation of 2. Of course, the inflection points where it starts to drop will be 22 minus 2, which is 20, and 22 plus 2, which is 24. Then question B. Find and interpret the probability that a randomly selected fertilized egg hatches in less than 18 days. So I'll draw the distribution, locate the number 22, and I want the probability that x, the number of days it takes to hatch, is less than 18. So I will locate 18 and I will shade the region less than 18. So for the region less than 18, this will be equal to, let's see, I need to set up my parameters, mean 22 and standard deviation 2. 22 and 2. So standard, and I want 22 and 2. and I want, in particular, less than or equal to 18. So less than or equal to 18. Hit enter. I have 0 0.0228. 0 0.0228. 0 0.0228. What does this probability mean? It means that if I multiply this by 100, for example, this will take me to about 2.28. This means that in 100 trials, for example, for this experiment, if I pick 100 of this, I expect about 2 of them to hatch in less than 18 days. Another way is to say that the probability that a randomly selected fertilized egg hatches in less than 18 days is 0.0228. Then question C. Find and interpret the probability that a randomly selected fertilized egg takes over 26 days to hatch. So, drawing this, I have the mean is 22, and you have 26. And we want to find the probability that it takes over 26 days. That will be more than 26. So probability that x is more than 26. Let us see what that probability would be. So I will go back to StatCrunch. I'll reset this to greater than or equal to 26. And I'm going to compute. That is 0.0228 again. So 0.0228. And next, we have to find the probability that a randomly selected fertilized egg hatches between 20 and 22 days. So again, you have 22, you have 20. So probability between 20 and 22, that will be equal to, let's see, we go here, we adjust this to between 20 and 22 days. Oops, let's see, 20 and 22 days. So you have 0.3413. This is 0.3413. Then, question E. Would it be unusual to hatch for an egg to hatch in less than 16 days? Why? I need to find the probability that it hatches in less than 16 days. That would be, going back, you have your 22, we have 16, and we want to find the area for less than 16 days. So in this case, this will be equal to what? Let us see. I'm going to go to the standard calculator, and I want less than or equal to 16 days and compute. This is 0.0013. So 0.0013. This probability is less than 0.05. Any probability that is less than 0.05 at this level, in this context, indicates an unusual event. So the answer to this is that yes, it is unusual because the probability is less than 0.05. So that brings us to the end of this first part of discussion on the normal probability distribution. In subsequent videos, we're going to learn more deeper problems on normal probability distribution.